Welcome. In this video, we want to have a quick recap of differentiation. In order to review it in context of physics, we want to go back to the motive behind the idea of differentiation. Why do we need to know about differentiation? Well, we noted that when we are interested in finding out the velocity of something over an interval, at best we could have the average velocity. And that average velocity was determined by the change in displacement over the amount of time it took to undergo that displacement. So the point is, over a certain interval, at best, we can obtain the average velocity. However, we are interested in finding out more about the motion because although we may know the interval, or rather the average velocity over a certain interval, we don't know the velocity of the particle or of the object at every instant. So if we want to find out how fast was the particle or object moving at every instant, we would basically need to make the time interval small as possible. Actually, there's a mathematical way of doing this, that is to take the limit as delta t approaches 0. Then that limit as delta t goes to 0 of this quotient actually is defined as a derivative. So therefore the velocity at every instant, instantaneous velocity is given by the time derivative of the position vector. So if we take the time derivative of a position vector, we obtain the instantaneous velocity. So we need to understand what this means. This is why we need to learn about differentiation. And just for clarity, this is not a ratio. This is not d divided by dt. Actually, this is an instruction instructing us to perform certain procedures onto this. And what are these procedures we are to take on this position vector? And this is the job of the next slide, to understand these procedures. So suppose you are given a polynomial function, a function of x, which if it's a polynomial of x, it will be a sum or a difference of powers of x, which in general we can write it as x to the power n. Of course, we could have maybe x to the power n minus, maybe x to the power n minus 1. We could have many, maybe a descending polynomial or an ascending polynomial. But the point is, every one of the terms of f, it will be something like x to the power n. So if we were to take a derivative of f, which this is, the instruction is you take the power of the current power of your polynomial and you multiply that the x with that initial power. And then you reduce its exponent by 1. So initially n was the power of this polynomial term, but now you bring down n here so that it multiplies the whole term, and then you reduce the power by 1. So as a result, we obtain something like this. This is the instruction. That is, you bring back x, except with its power reduced by 1, and now this term is multiplied by n, which used to be the power. And then the limit or the caveat is that n should not be equal to 0. This rule is applicable for as long as n is not equal to 0. When n is equal to 0, we will have another rule for that. But for now, this is the rule of differentiation, polynomial differentiation, is that you reduce the power by 1 and you multiply that term by the old power, which is n. Now, if you have two functions that are being added or subtracted from one another, and you are required to take the derivative of them, of this expression, this is the rule of how you take the derivative. The derivative of the sum is actually the sum of the individual derivatives. So that is, the derivative here is distributive. So it's the same whether you first add the functions together and then take a derivative, Or you could take the individual derivatives and then add them afterwards. Of course, the same is true for the difference. But it doesn't matter which you do first. You could either add and then take the derivative, or you could take the derivatives first and then add. So the point is differentiation commutes with this addition or subtraction. Now what happens if n here is 0, that is the power of x is 0? Well, that would be x, any x raised to the power 0, provided that your x is real, that means it's going to be 1, which means your expression here would be independent of x. This instruction tells us take a derivative of whatever comes to the front with respect to x. But this thing here is independent of x, that is, it doesn't change with respect to x. So therefore, its changes with respect to x will be 0. So any constant or anything that is independent of x, and the derivative of that thing will always be 0. And then the final rule which we will need is to consider if you have some number or some constant which is independent of x multiplying a term or a polynomial term which does depend on x. How do we take a derivative of that? Well, the derivative of this is the same as if you avoided or you did not pay any attention to the term a, and you simply moved it outside the derivative, and then you take the derivative of x to the power n. So a derivative of something that's multiplied by a is the same as a multiplying the derivative of that polynomial. So the point is, this thing is immune to the effects of the derivative when it's multiplied by x to the power n. And if we were to perform this instruction, obviously over here, for this term, for this part of the expression, we would use the first rule, which is that, and then the result we would multiply by a. So that's exactly what we have done here. We have this thing here, which comes from there, and we've multiplied by a. And again, the key here is that it has to be such that n is not equal to 0. So let's consider an example of this, which includes all these rules. So suppose we had a function f of x, which function is given by 2xy squared plus 3 over x squared plus 7. And we were to take the derivative of f of x. So the first rule we would need to use here is to consider that f is a sum of different functions. So the derivative of f is the same as the sum of the individual derivatives, of the individual terms. It's the sum of the derivative of each of the terms. So the point is, we can happily do this. We could happily say it's going to be the derivative of the first term, which is 2xy squared, plus the derivative of the second term, which is 3 over x squared, plus the derivative of the last term, which is 7. So what we have used here is the first or the second rule, that is that the derivative over the derivative of the sum is equal to the sum of the derivatives. So f itself is a sum of functions. When we take the derivative of f, we end up with the derivative of the sum of the individual derivatives. Okay, so let's go ahead and take a derivative of this term. Notice this term, it is multiplied by two things that don't depend on x. 2 is a number, it doesn't depend on x, and y doesn't depend on x. So these two terms, or these two variables and constant, are independent of x, so we can move them outside the derivative. So we could write this as 2y squared d of x, derivative of x on x. So the rule we have used here is this rule that when you have something that's multiplying, that is independent of x, but multiplying something that depends on x, that thing can move out of the derivative. That's exactly what we did. 2y squared are independent of x, so we've moved them outside of the derivative. And then for this term, for this middle term, first what we need to do is to take this x squared, which is a denominator, and move it upstairs to be a numerator. So let's rewrite that so that we have d dx of 3x to the minus 2. And here it's minus 2 because when it was at the bottom of the dividing line of the divisor, it was positive. So when we take it upstairs, it becomes negative. And then finally, we will have d dx of 7. And we can already simplify this part, because this part, we have something that is independent of x. Actually, the power of x here is 0. And the rule for when the power of x is 0 was the third rule. That is, the derivative of anything that's independent of x is equals to 0. So this last term is going to be 0. Because this thing doesn't depend on x. It doesn't change with x. Then let's go back to the first term. The first term, what we have left is 2y squared outside. Now, what is the derivative with respect to x of x? Well, let's use the rule first. The rule is we have to reduce the power of x by 1. So the initial power of x is 1. This is the power of x there is 1. So we have x to the power 1, but we reduce it by 1. And then we take the old power and multiply this term, so times 1. So this is what we have by using the rules. And let's do the same for this middle term. 3 here is independent of x, so we can move it outside the derivative. So 3 can be outside the derivative. This will leave us with this. And what is the derivative of x to the power minus 2? Well, we bring back the x and its power, but we reduce its power by 1. And then we multiply this term by the old power. The old power was minus 2, so we end up with minus 2, multiplying this thing here. So, and then obviously this is going to be plus 0 because this last term was equal to 0. So let's clean this up. Look at what we obtain. We obtain that this is 2y squared. The reason why this is 2y squared is that the power here is going to be 0. 1 minus 1 is 0. X to the power 0 is 1. So we end up with y squared. What about the second term? The second term we're going to obtain minus 6 x to the power minus 3. The reason for this is we have 3 multiplying minus 2, so we end up with minus 6. And the power of x is minus 2 minus 1. Obviously, that will give us minus 3. So what we have over here is the derivative of f of x. This is how we use these rules to take care of derivatives. We will use this in the context of physics whenever we have supplied a position vector as a function of time. We will use this to find the velocity, because the velocity will be the time derivative of the position function. And also we will use it to find the acceleration vector. The acceleration vector instantaneously will be defined as the time derivative of the velocity vector. So I hope this gives you a bit of a summary of why we need differentiation and how to use it, especially for polynomial functions. See you in the next video.